Bismillahirrahmanirrahim. Today is our lecture number 24. Chapter is chapter 2 about differentiation, and our today's topic is series expansion of function and exercise. And at the end of our lecture, I will do some questions from the exercise, and the exercise is 2.8. Now we start our lecture. Taylor expansion, Taylor series expansion of functions. Now in this case, if the first thing is if f is defined. Defined means we take such type of function which should be defined. Defined means it must exist, it has some specific value, and it does not undefined at any specific point. Now the function is defined in interval containing point A, means this function must be defined on this point. And the second thing, its derivatives of all orders exist at that specific point. And then we can expand our function, like expand as, if these two conditions hold, then we can expand our function like f of x is equals to f of a plus f prime of a into x minus a plus f double prime of a into x minus a square. This is the function at this point a. Then this is the first derivative with first degree of this factor. Second derivative, second degree of this factor, plus third derivative, power cube of this factor, plus up to plus nth derivative. Sorry, here we have 2 factorial, 3 factorial, and then nth factorial with x minus a power n, plus up to so on. Now you can see the symmetry in all terms. Here we have no derivative, simple function at this specific point. First derivative with this factor, and this factor has the power 1 with 1 factorial. Then second derivative and 2 factorial, this factor has power 2, and up to nth term and up to so on plus. Now if we suppose that let us suppose that if f of x is equals to a naught and a1 into x minus a plus a2 into x minus a square plus a3 into x minus a cube plus up to n into an into x minus a power n plus up to so on. It means obviously if we say that this f of x is equals to this series also, and if we compare these both terms, then obviously f of a is equals to a naught. This f of a must be equals to, because both are the series of f of x. This is equals to f of x and this is also equals to f of x. So obviously if these are both are the same series, then this first term must be equals to this a naught. And we say that if we take the first derivative of or this function, this first f of x, If we take the first derivative of or, okay, I just want to explain you one thing. So I will give you a little break. If I take, okay, now this is the rough work. For rough work, I will show you something. If I have f prime of x, I am taking the first derivative of this series. This, I can say it's equation number 1. If I take the first derivative of equation number 1, so what will happen? F prime of x is equals to f of a is a function at some number, some any real number. So it must be equals to 0. And when we take the derivative of second, first what will happen? F double prime of a f prime of a into 1 minus 0 plus f double prime of a divided by 2 factorial into, first we solve the power. I'm taking the derivative of this term, 2 into x minus a, 2 minus 1, and then the derivative of inside means 1 minus 0 plus f triple prime of a divided by 3 factorial into 3x minus a power 3 minus 1, then x, then 1 minus a, plus up to plus f n of a n factorial into n x minus a power n minus 1 into 1. And if I take its second derivative, so what will happen? This term again become, this is already 0 and this will also become equals to 0. And then we have 2 by 2 factorial into f double prime of a, I am taking the derivative of this term, and then 1 minus a, 1 minus 0, sorry, then 3 by 3 factorial f triple prime of a into x minus a square. Here we have square means here we have 2 also, 2 into this plus up to n by n factorial into n minus a fn of a into x minus a power n minus 2 plus up to so on. Means if I, and if I simplify this, I will get what? I will get 2 factorial is equal to 2 factorial. So here I have f double prime of a plus 6 and 6. They will be cancelled with each other. And I have f triple prime of a into x minus a plus n into n minus 1, n into n minus 1 into n minus 2 factorial f n of a into x minus a power n minus 2. So they both will be cancelled. And if we this is the second derivative, and if I find the third derivative, and third derivative, and this process will be continuous. Now if, so this is what I want to show you, that how we get the, now come back to your theorem. So f prime of x is equals to, we can say that from this, f prime of x is equals to f prime of a, means we have what value? F prime of a is equals to, that's why I am saying you that if f prime of a, f prime of a is equals to this a1 plus this 2a2 into x minus a, then up to, if I combine all these terms. So this is what I want to show you, that how we get these all values. And if we put x is equals to a, so what will happen if I put all these values at x is equals to 0, x is equals to a, so all values will be vanishes. So that's why I'm saying that if I write here like f prime of x is equals to a1 plus 2a1 into x minus a plus 3a3 into x minus a whole square plus up to n into x minus a power n minus 1 plus up to so on. Then f double prime of x is equals to 2a2 plus 6a3 plus x minus a plus up to plus n into n minus 1 a n into x minus a power n minus 2. So these are all the terms. So I can find different derivatives on all these functions. But you keep in your mind that when I put x is equals to a, what will happen? Look at here. X, here we have x. If I put a minus a, this term will be 0, this term will be 0, and all other, just we obtain these first terms from all derivatives, and that's why we can say that, what we say, the first derivative, if I put x is equals to a, what we get? We get f is equals to f prime of a is equals to a1, f double prime of a is equals to 2a2, f triple prime of a is equals to f triple prime, or from here we can write, means when I write f double prime of a2, you can write it f double prime of a divided by 2 factorial is equals to a2, and then f triple prime of a is equals to 6a3. So we can write it like f triple prime of a divided by 3 factorial is equals to a3, and so on. So that's why we can write it like, if we say that f of x is equals, we substitute all these values in our equation 1, and then we get f of x is equals to f of a plus f prime of a into x minus a plus f double prime of a divided by 2 factorial into x minus a square plus f n of a divided by n factorial into x minus a and n plus up to so on. So this is your equation number a. Now this expansion is known as Taylor series. Taylor series, Taylor series, and for Taylor series for f at x is equals to a, and this expansion is valid when if it is convergent, means and valid if it is convergent, means if this series is convergent, then we can say that this expansion is a Taylor series for f at x is equals to a, and the expansion is only valid if it is convergent. Now the subcase of this series is what is if we take if we have a is equals to 0, means instead of x is equals to a, if we put x is equals to 0, then the above expansion will becomes equals to f of x is equals to f of 0 plus f prime of 0 plus f prime of 0 x into f prime of 0, and then x square into f double prime of 0 divided by 2 factorial x cube by 3 factorial f triple prime of 0 plus up to uh, x power n fn of 0 divided by n factorial plus up to so on. And then we say that this is a Maclaurin's series for f at x is equals to 0. And if we, this is the Maclaurin series, this is the, this series is, this series is, this series is Maclaurin series, Maclaurin series for f at x is equals to 0. Now if we this, replace this x by x plus h and a by x, means we replace x by x plus h and a by this x. So our equation a will become equals to f of x plus h is equals to f of x plus f prime of x h plus f double prime of x 2 factorial h square plus f n of x n factorial into h n. So this is, and plus up to so on. So this is your equation number B, and this expansion which I have written in equation number B is termed as Taylor theorem. When we write this expansion in this such type of series, in such type of expansion as I have written in equation number B, this expansion is now known as Taylor theorem, and we can we can be stated as if x and h are two independent quantities and f of x plus h can be expanded in ascending power of h as an infinite series, then we can write such type of expansion. Here you can see that h is the ascending power of h as in infinite. This series is infinite series, and you can see the power of x is increases term by term. Here we have h naught, h1, h square up to n plus up to so on. Now in this all discussion, you can see what is Maclaurin series, what is Taylor series, and finally which statement is known as Taylor theorem. Now this is the theory of all this Taylor and Maclaurin. Now we discuss the question, the application of these all expansions. Now you see the example, that is example number 1 at page 99 of your book. Here we have find the Taylor series. We have to find the Taylor series expansion of function log of 1 plus x and at x is equals to 2. Now this is our f of x and this is x is equals to a. Here we have the value of a is equals to 2. Now we start the solution. Now let's say our f of x is equals to what? Log of 1 plus x. and then when we find its derivative as in Taylor's expansion, the first thing which we have discussed, that the function must be defined at the given point. So here we have the point is 2. So first we check whether our function is defined or not. So log of 1 plus 2, and that is log of 3. Okay. The second thing, we have to find the derivatives. We have to find the derivative. The second thing which we have discussed, that the first thing is the function must be defined on the specific point at the specific point given point, and all the derivatives must exist at that point. So what we do, we have to find the derivatives. Okay, now as f of x is this, so f prime of x must be equals to 1 by, we have studied that the log function is 1 by 1 plus x, and then we find the derivative of this d by dx of 1 plus x. Okay, then 1 by 1 plus x is equals to 0 plus 1, means first derivative is equals to 1 plus x. Again differentiate f double prime of x, means here we have to apply the quotient rule, but instead of quotient rule, if I write it like f minus 1 d by dx of this. So first we solve its power 1 plus x minus 1 into 0 plus 1. So we have minus 1 divided by 1 plus x square is the second derivative of our function. And if we find the third derivative, f triple prime find of x, f triple prime of x, then we have minus 1 minus 2 into 1 plus x power minus 3, and we write it like 2 into 1 plus x into minus 3, or 2 divided by 1 plus x power cube. Now these are the derivatives. I will write it again here without these calculations. We find f prime of x, the value of f prime of x is 1 divided by 1 plus x. And the second derivative of x is minus 1 into 1 plus x power minus 2. The third derivative is minus 1 into minus 2 into 1 plus x power minus 3. So these all are the derivatives, and if we find, we have to find all the derivatives up to because this function is in up to, we can expand Taylor expansion up to infinity. So that's why as much as derivatives you can find. Now here I have find the, if I write the fourth derivative also, so fourth derivative will be equals to minus 1 into minus 2 into minus 3 into 1 plus x power minus 4. Okay. Now the thing is, we have to this is the first derivative, but we have to find the value at point x is equals to a. So here we have x is equals to 2. So first we check the value of first derivative at point 2. So 1 into 1 plus 1 means 1 by 2. 1 by 2. No, not 1 by 2, 1 by 3. The first derivative is equals to 1 by 3. Now second derivative at point 2 is equals to minus 1 into 1 plus 2 minus 2, means we can write it minus 1 into 3 power minus 2, means minus 1 by 9. the third derivative at point 2, or we write it like okay, now the third derivative is equals to at point 2 is now minus 1 and minus 2 plus 2, means here we have 2 into 1 plus 2 minus 3 is equals to 2 divided by 27, and the fourth derivative is equals to minus 6 divided by 81. Okay, now we substitute all values in our Taylor series expansion. So the Taylor's expansion is Taylor's series expansion is f of x is equals to f of a plus f prime of a into x minus a plus f double prime of a by 2 factorial into x minus a square plus f triple prime of a divided by 3 factorial into x minus a square plus up to so on. And when now we substitute our value, f of x is equals to log 1 plus x, and f of a is equals to log of 3. You can see the values, and I'm just writing, substituting the value, and f prime of a is equals to f prime of a is equals to 1 by 3 into x minus a. Instead of writing a, I will write here 2 plus f double prime of a is equals to f double prime of a is equals to minus 1 by 9. The value was minus 1 by 9 divided by 2 factorial into x minus 2 square plus f triple prime of a is equals to 2 divided by 27 divided by 3 factorial into x minus a whole square plus up to so on. Now this is log of 3 plus x minus 2 and 1 into 3. If I write 1 into 3, thus x minus 2 square minus sign is here, minus x minus 2 square divided by 2 factorial into 3 square plus x minus 2, so here I write it, x minus 2 power cube, sorry, this is a mistake, okay, cube divided by 4 into third is 3 into 3 cube. Okay, minus up to so on. This is the answer of our question, and that's it. Now I start the exercise. You can see some questions from exercise. Now here we have exercise 2.8. Apply the Maclaurin series expansion to prove that. Question number 1. Log of 1 plus x is equals to x minus x square by 2, x cube by 3, x 4 by 4 plus up to so on. So this is the first question from exercise 2.8. Now I start the solution and we have to apply the Maclaurin series. Okay. Now log of f of x is equals to log of 1 plus x. Now differentiate with respect to x. So f prime of x is equals to 1 plus x minus 1. In the example, I have find different derivatives, and here luckily the function is same, so no need to show you the whole procedure how I find the derivative. So now f double prime of x is equals to minus 1 into 1 plus x power minus 2. F triple prime of x is equals to 2 into 1 plus x power minus 3. And f4 derivative is minus 6 into 1 plus x power minus 4. And here we have, as I've told you, when we put x is equals to 0 in our Taylor series, we get the Maclaurin's expansion. So here we have to find the Maclaurin, so we put x is equals to 0. So f of 0 is equals to, in this f of 0 is equals to log of 1 plus 0, means log of 1, and we know that log of 1 is equals to 0. Now f prime of 0. F prime of 0 is this function, means here we have 1 plus 0 power minus 1. 1 power minus 1 is equals to 1, and f double prime of 0 is equals to, this is the double prime of 0, minus into 1 plus 0 power minus 2, and this is equals to minus 1. F triple prime of 0 is equals to 2 into 1 plus 0 power minus 3, means 2 into 1 power minus 3, and that is equals to 2. And f4 of 0 is equals to minus 6, 1 plus 0 power minus 4. So here we have minus 6. You just write here the Maclaurin series and put all these values, means f of x is equals to f of 0 plus f prime of 0 plus f double prime of 0, 2 factorial, f triple prime of 0, 3 factorial, plus here we have x, then x square, here x cube, then x4 and f4 of 0 plus 4 factorial plus up to so on. So when we put the value f of 0 is 0 plus 1 into x plus minus 1 by 2 x square plus 2 by 6 x cube plus minus 6 by 24 x4 plus up to so on. And when you simplify it, x minus x square by 2, x cube by 3, x4 by 4 plus up to so on. So this is the proof of your first part. So same thing is happened in all other questions. There is no change. All the questions are very easy to solve. I will solve it one more question, that is the fourth part. You can see the fourth part is exponential of x is equals to 1 plus x square by 2 factorial x cube by 3 factorial plus up to so on. This is also the very simple question. Now I start the solution of this part. Solution. Now f of x is equals to exponential of x. So first we differentiate it with respect to x. Now f prime of x, exponential of x. F double prime of x, again exponential of x. F triple prime of x, again exponential of x, and up to so on. And if you check all these values at point 0, so f of 0 is equals to exponential 0 1, f prime of 0 is equals to exponential of 0 1, f double prime of 0 is exponential of 0 1, f triple prime of 0 is equals to exponential of 0. Exponential of 0 is equals to 1. F fourth of 0 is equals to exponential of 0 is 1, up to so on. So you just apply the values in equation number 1 and get the final result. Here you write the Maclaurin's expansion, and f of x is equals to f of 0 plus f prime of 0, and then up to so on, and just put the values. Now we move to question number 2. Question number 2 is show that cos x plus h is equals to. Question number 2 is cos x plus h is equals to cos of x minus h sin of x minus h square by 2 factorial cos of x plus h cube divided by 3 factorial sin of x plus up to so on, and evaluate it at cos 61 degree. Okay, now we start the solution as we say that let f of x is equals to f of x plus h is equals to, here we have x plus h, that's why I've written f of x plus h is equals to cos x plus h, the first term, right? Now f of x, no, not the first, sorry, not the first term. Here this is our f of x, this is our f of x. So here we have the increment, so that's why f of x plus h is equals to cos of x plus h. Okay, now means if I write f of x, it should be cos of x. Now differentiate with respect to x. So if we differentiate the first derivative f prime of x, we know that cos of x is equals to minus sin of x, and f double prime of x is equals to minus cos of x. F triple prime of x is equals to minus and minus plus sin of x. Now in this case we have to apply the Taylor's theorem. Why we applied the Taylor's theorem? Because in the statement you can see we have cos x plus h, and in the start of my lecture I have told you whenever we have x plus h, then it means that we have two variables, x and h both, and whenever in our expansion we have x plus h type of function, it means here we have to apply the Taylor's theorem. So just write the statement of Taylor's theorem, and that is f of x plus h is equals to f of x, f prime of x h, f double prime of x 2 factorial h square, f triple prime of x 3 factorial h cube plus up to so on. Now f of x is, what is the value of f of x? That is cos of x. F prime of x is minus sin of x. H remains same. F triple prime of x is minus cos of x by 2 factorial and h square. And sin of x by 3 factorial h cube. Plus you can see all these values from here. Okay. Now now f of x is equals to cos of x plus h, and this is cos of x minus h sin of x minus h square by 2 factorial cos of x plus h cube by 3 factorial sin of x up to so on. So from this step we have this equation represents the Taylor's theorem. But the last part of our question was that evaluate at cos of 61 degree, means we have to, one step is left, and that is we have to evaluate at 61 degree. So Let's say x is equals to 60 degree, h is equals to 1 degree, means pi by 180 radian is equals to 0.101745. Okay, this is now in radian. So when we write cos 60 degree plus 1 degree is equals to, just write in at the place of x is equals to 60 and h is equals to 1 degree. So cos of 60 degree minus, here we have to use this value, h is equals to 0.101745 and into sine 60 degree minus again 0.101745 square divided by 2 factorial. So cos of 60 degree plus up to so on. Now the rest of calculation you can do. You just write down the values 6 cos 60 sin 60 and just calculate it, and I will tell you the answer, and that is, the answer is cos of 61 degree is equals to 0.4848 approximately, right? The same thing in question number 3 also you can see. In question number 3 of exercise, question number 3, sorry, question number 3 is, show that 2 power x plus h is equals to 2x 1 plus log of 2 h plus log of 2 square h square 2 factorial log of 2 cube h cube 3 factorial up to so on. So what you have to do, just take f of x plus h is equals to 2 power x plus h, right? And it means that f of x is equals to just 2 power x, no h. Just differentiate with respect to x. So when you differentiate it with respect to x, means first derivative will be equals to, here we have f of x is equals to 2 power x. Okay, 2 power x means we have 2x and then log of 2. This is the derivative of 2 power x into, or you may write it like log of 2 into 2 power x. Okay, now again the second derivative. Now here we have the two functions. So first function is derivative d by dx of log of 2 remains same, d by dx of 2 power x, then plus 2 power x remains same, d by dx of log of 2. So log of 2 is same, and when we differentiate it, we have 2x into log of 2. 2x into log of 2 plus 0. So we can write 2x into log of 2 square, or log of 2 square into 2 power x. Sorry, this is x. Okay. Again, the third derivative is again log of 2 power cube into 2 into x up to so on, and you can find some more derivative if you want. but up to 3 derivatives it's enough in these questions. So we apply the Taylor theorem. Apply Taylor's theorem. Taylor's theorem. F of x plus h, f of x, f prime of x plus f double prime of x 2 factorial h square f triple prime of x h cube 3 factorial plus up to so on. And when you apply the values, you get 2x 1 plus log of 2 h log of 2 square h square 2 plus log of 2 cube 3 factorial h cube plus up to so on. And where we have 2x plus. So this is the proof of your question number 3. And in your book, in exercise 2.8, we have these questions, and just these 3 questions, and this exercise is complete. And even then, if you have any problem, you can contact me on my WhatsApp number. And one thing more, in all these questions, you just keep in your mind the 3 things. The first thing is Taylor expansion, then Maclaurin's expansion, and then the Taylor's theorem. In the start of my lecture, I have show you how the Taylor expansion is how we derive the Taylor's expansion, but you just understand what is Taylor expansion and when Taylor's expansion converted into Maclaurin's expansion, and how the Taylor's theorem is different from the Taylor's expansion. What is the step? So simply we have Taylor's expansion, and when we put x is equals to 0, we get Maclaurin's, and when we have two independent variable x and h, then we say that our theorem or expansion is converted into theorem. So this is the theorem. Here we have f of x plus h instead of just x. So these are the main points. Now this is the end of my today's lecture. Thank you very much.